So some of the terminology might be a little bit confusing. So I have set up here just an example of what your guys' like initial setup should be. So let's look at the function header for something like make particle map here. So make particle map takes in a width and a height. So that width and height should correspond to your array's width and height. So this will be the width and this will be the height. Note it grows downwards, so this is 0, and this last index is whatever it happens to be, n. And that's because we're working with arrays. So that's just something to keep in mind. Now this window x and window y, this is where you're going to be dropping your particles initially, and we'll take a look at that later. Essentially, this is going to be a center coordinate, and that goes hand in hand with this next one, the radius. So you're going to be defining a center coordinate, and then the radius for which the drop zone, which is the circle, should be. For simplicity's sake, I am going with a box. So just know, radius is how far out you go, and the width, or the window X and window Y, are the middle of the drop window. All right. Oops, spoilers there. And then we take in two more things, the number of particles and the max life. And those are pretty self-explanatory. So for this one, I chose just 2 particles with 5 max lives. And let's go over sort of how you're going to be doing the particle drop. So initially what we'll do is we'll choose a random location inside our drop window. And you can find a calculation for that. I believe it is all the way up here. Yes. So this is how you're going to be calculating that random location inside the drop window. So what we'll do is we'll start by dropping our first particle. When we drop a particle, what we're going to do is we're going to increment the index, or increment the value at its index. So for this, we're assuming this is just a bog standard array with everything initialized to 0. So when we drop the first particle, let's randomly choose this location here. We're going to change whatever value happened to be here, which in this case is 0. We're going to increment it by 1 and drop our particle. And then we're going to decrement our lives from 5 to now 4. All right. So now we have to choose a random location to move to. And to do that, we'll inspect the Moore neighborhood. So particles can't roll to something with a higher value. So if I had like a 2 here, this particle couldn't roll to this index here. All right? But in this case, this is our first one, so this is all zeros. We can roll wherever we want to. Let's say our algorithm randomly selected this index to roll to now. So we decrement the lives, and we move over, and now we check this Moore neighborhood. And again, we just pick some random coordinate to move to. So we'll move over here. Decrement again, and check this guy's Moore neighborhood. And we'll keep rolling around. Let's say he chose there to move to. So we'll lock this and move over here. And let's see, that was what? 1, 2, 3, 4. So this is the last life. It's going to move here. Now, our particle only had 5 lives, which means it is dead. So when we kill a particle, what we do is we decrement the number of particles that are left available. So we started with 2, and now we only have 1 particle left. And we're going to choose another random location inside this drop zone. So again, it's that same calculation that you saw up here to pick a random coordinate. And let's move to right here. So it's the same sort of algorithm, same deal, where we just look at the Moore neighborhood of this one, pick a random spot to move there. All right, so when we're choosing a location to randomly move to, we have to sort of think about the efficiency of our algorithm. The random selection is going to have probably the largest impact on your performance out of any of the algorithms in this assignment. So I have set up here just an example of a 6 that's landlocked by a bunch of 9s and a 2. So our only valid move would be to go from this 6 over to the 2. Now, what I have set up here is a demo of the naive approach, sort of the easy way to do it, where all we do is choose just some sort of random value to move to, and check if it is something that we're allowed to move to. If it isn't, then we'll loop again, and if it is, we'll break out of the loop and print out how many times it took to find that location. So this is the exact situation that I have shown right up here, where it's that 6 landlocked by a bunch of 9s, and then this one singular 2. So when I run this, it is hopefully going to do what I want. That one took 1 attempt. All right, nice and efficient. That one took 7 attempts. Let's see, 2, 6 attempts, 6 attempts. So even though there's only one valid move, it's still taking us a lot of times to find this, right? That one got up to 11. Most of these are in the 7s. And I've seen a couple of these take 21 times to find, which honestly doesn't seem too bad, right? I'm running this and it's pretty much instant. But you have to consider, we're not just doing this once and isolated, right? I have this whole array. I can be dropping maybe 10,000 particles 10,000 times, right? So that's quite a few times that we're going to be checking through this, that we're going to be running that random selection algorithm. So if it's taking somewhere like 11 times to find a single value, we're going to have huge issues with the efficiency. I'm going to leave that up to you guys to figure out how to solve, if you even want to solve it. Doing it this way is okay, but it really isn't efficient. This is something that you should definitely improve on. The goal for this is to only choose from valid moves. That's what you should be working towards with this random selection algorithm.